那么，各位线上的老师和同学们，大家晚上好。非常荣幸，我们邀请到了这个常国庆老师为我们组织这个超快激光和非线性光学专题。Okay, good evening, everyone. So, tonight, we start the new subject of the photonics open course. And this subject is the ultrafast laser and the nonlinear optics, organized by Professor Chang Guoqing. And he organized this session with 8 talks from May 19 to the July 3rd. So almost 2 months. We really appreciate the hard work and the collaborations from all the speakers. And tonight is the first talk given by Professor Yuri. Actually, Yuri is very famous, and his talk is Metaphotonics and Metaphotonics. So later on, Professor Chang will host Yuri's talk. Okay, Professor Chang. Generally, our course can be 2 sessions. Each session can be about 45 minutes, and we will have a 10 minutes break in between. At the last, Professor Chang will help to communicate on behalf of the readers and on behalf of all the attendants with Professor Yuri. Okay, so that's the arrangement.
Okay, thank you for the introduction. Now it's my time to introduce Professor Yuri Kivshar. Yuri received a PhD degree in 1984 in Ukraine. From 1989 to 1993, he worked at several research centers in both USA and Europe. And he moved to Australia in 1993, where he established the Nonlinear Physics Center. His research interest includes nonlinear physics, metamaterials, and nanophotonics. He is a fellow of the Australian Academy of Science, OIC, APS, SPIE, and ILP. He received many national and international awards. The list is really long. I won't mention all of them. I just want to emphasize he received the Harry Maser Medal, the Humboldt Research Award, and SPIE Mosey Award. Okay, now let's welcome Yuri to give us the lecture on Mie-resonance and metaphotonics.
Thank you very much for introduction. I still not very familiar with the format, so I'm not making breaks. I have about
yeah, Yuri, it's very flexible. You don't have to make a break as long. Yeah, it's just up to you. You can have like a 5-minute or 10-minute break in between, or you just finish the whole lecture. Then we can continue with.
I have something like up to 1 hour, and if possible, I may stay and continue if you don't mind. Yeah.
Okay. Yeah, sure, no problem. It's very flexible, the format.
Okay. Thank you very much for inviting me. I'm not sure it's an undergraduate talk, but still people may get some general information and see how we may proceed to more sophisticated problems. First of all, I'm currently in Australia. I know Australia is not the best friend of China at the moment, but I really hope things will change. And I also associated with ITMO University in St. Petersburg in Russia since 2010. Australia is a big piece of territory. As you can see, it's a very, very big land, not very well cultivated, but it's larger than all European Union. And if you look at the number of people immigrated to Australia by country of birth in 2018, you see it's dominated by British, but China is actually doing very well, and I hope it will be continuing. What is important personally for me is that almost 30% people were born overseas, so it's it's much easier to feel for foreigners in the country than particularly in Germany when I stayed there 2 years before coming here. What is famous about China, of course, you know, kangaroos, but there are a few facts which I wanted to mention, which is not very known. For example, Melbourne is the second city in Australia. I actually traveling tomorrow there. And it's full of Greeks and Italians. So there are several, even streets full of Italian restaurants, which are quite famous in the country. That basically was a big immigration after Second World War from poor European countries. Also interesting fact that, of course, you can expect that we have a lot of beaches. Almost everywhere you go, approaching the coast, you see very nice patches of sand and a nice beach environment. But what is absolutely less usual knowledge about Australia is that it's not koalas and kangaroo, but actually a huge population of camels. Camels were taken to Australia to actually investigate central part when we have a huge desert. And currently we found the second home and actually run around, and almost 800,000 camels running in the country. So still in this country, we do some science. This is a camel sign, but it's somewhere in the middle of Australia. And today I will be talking about a very new field, which we now term Mie-resonance. And I will explain what is this. But to introduce these new developments, I need discuss all problems. The very big field which flourished during last 10-20 years is so-called plasmonics. Plasmonics is associated with a very special type of excitation. So when electromagnetic field approaches metallic surface, it hybridizes with free electrons in metals and create a special type of state, hybrid state. So it's a combination of electric field here and electron wave functions in the metals. And this is known as the surface plasmon polaritons. This new type of hybrid modes of waves can allow light squeeze very close to the surfaces. And it was a huge success in plasmonics because it allows to actually go to subwavelength. You know, this light is restricted by diffraction limit, and it's impossible to squeeze light in the very small spots. But here, because we transform actually light, like electromagnetic waves, to surface plasmon polaritons, we can do it. And it was a lot of activities studying waves as the interface of these insulators and conductors, different modes of metallic particles. And in experiments, this is observed the specific different colors which are produced by these excited modes. The physics of these modes is actually separation of charges inside of metal object, metal particles, when electromagnetic waves create effective dipole. So basically, the entire field of plasmonics is driven by electric field and electric dipoles, electric resonances. Some years ago, we observed appearance of entirely new field of physics and electromagnetic theory, which is called metamaterials. Meta is a Greek word which means beyond, and this means that it's materials beyond anything known in nature. The concept of these materials is actually relies on two types of resonances, electric and magnetic resonances. So we can immediately ask, what is the point to discuss magnetic resonances if light does not have magnetic properties, and materials usually used in optics are non-magnetic, unless we look at the specific magnetic materials. So these are magnetic response associated with magnetic component of electromagnetic waves, and it's usually fabricated through specific artificial structures. So to get metamaterials, we need two types of elements. We need electric dipoles. This is metallic rods, which allows you to separate charges when you apply electromagnetic wave. And this is splitter resonators, which create magnetic moment. Electrons in these metals oscillate freely, and we create magnetic moment when material is excited by electromagnetic waves, and this magnetic moment is not given by material, it's excited externally. But this response, magnetic and electric, is extremely important because when we look at the arrangement of these elements, we can basically modify response properties of any artificial materials, generating different materials with different magnetic and electric properties, mu and epsilon, which enters Maxwell equations. So the first idea actually to change epsilon and mu and look at the this most important thing is that you can usual common materials have a mu response to magnetic field positive and epsilon positive. But when we engineer structures by creating this meta atoms or resonant elements, we can enter any point of this plane, and the most interesting part is a negative index material. So in most of the textbook, of course, you read that n, refractive index of materials, is positive, but it's not so, because in the Maxwell equation we don't define n, refractive index, we define n squared, and to get n you need to take square root, and when you take square root there are two options, plus and minus, and we can actually introduce entire class of materials which will have a negative index. And that was the subject of the so-called negative index materials. The first, it was, I don't have a Chinese version, this is the Russian version, was introduced by Victor Veselago in 1968, who just wrote a very strange theoretical paper saying that what will happen if materials will have both epsilon and mu negative. That was back to 1968. And this is Victor Veselago. Unfortunately, he passed away a few years ago. So we know that Nobel Prize is given only a life candidate. So we missed the possibility to have a Nobel Prize. So we will see in the future what will happen. So he published this paper in 1968. And only in 2000, a group from San Diego, from California, actually publicated the first structure. This is a microwave structure. You can see gigahertz frequencies, and elements of the structure are made of these two spring rings and rods. So basically, this is purely magnetic response, and this is magnetic and electric response. And they basically confirm that there is a possibility to design material which will have simultaneously negative permeability and permittivity, so simultaneously negative mu and epsilon. That was the first paper in 2000, only 20 years ago, and that's boosted the field dramatically with many interesting discoveries and ideas. So what is the concept of these materials? This concept, basically, after we engineer these elements, we look at the materials like composition of these elements, exactly like nature does. So what we have a solid or liquid, whatever, let's talk about solid, and the condensed matter or solid state objects are composed of atoms. So basically, if you touch some even desk here, you don't feel the atoms. And the idea is that they are too small, that your fingers too big, so you don't feel them. But these are actually elementary composition units of this particular glass prism. So the same concept was applied from the very beginning to metamaterials. This is a film covered by this structure. It's a flexible field, and this field consists of small elements. These particular elements show on the split rings like a horseshoe type of shapes made of metals, and when light illuminated on such structure, it excites magnetic resonances and completely change response of the structures to electromagnetic wave. But you still, if you look at this piece of glass, it's a flexible glass covered by this new material. You don't see any elements because they are too small. They are few hundred nanometers small, and of course you do not differentiate microscopic structures similar to what you have in nature. So initial ideas of the founders of the field was that we actually look at electromagnetic waves which much larger than scale. We introduce average parameters and we describe the entire structures by using average parameters. And what happened from these new properties? People generated many great ideas. We generated many new concepts. These new ideas entered very high profile fields. There was a lot of interest in newspapers. You see what kind of concept? Optical magnetism, so magnetism of materials which are not magnetic. So it can be arranged from creating microstructures. Negative index, I already mentioned. Negative indexes contradict to all textbooks which were published before. This clocking, invisibility clocking, was very popular topic in China. Some time ago, many groups were fascinated by development of these clocks, probably because of creating invisibility of different objects. Optical circuits, some correspondence to electronic circuits, superlensing, hyperlensing, chiral effect due to meta atoms. It was a lot of interesting discussions. You see that it's after 2000, it was slowly evolving, about 10 years. And initially, people just fabricated structures with specific structure properties and just studied them. And then about 10, 15 years ago, this field slowly moved to new stage, people looking at active, tunable, and reconfigurable metamaterials to find applications. One of the concepts behind metamaterials is so-called invisibility clocking, possibility to hide object by covering them by special type of material. What kind of material is that? So if I look at the Maxwell equation, we can find that Maxwell equation can be transformed to different shapes by simultaneous changing not only wave properties, but also material properties. So we can create a ring here with open space there, and this ring can be arranged in the way to bend light around this hole, this open void. So this means that basically you may hide object here inside, and observer will look at and will not see object because rays passing that direction and that direction will not go to the cavity where this object is hiding. There was a lot of hype associated with that, but you may immediately ask, what is the point? Where is the metamaterials? The very important thing is that when you transform Maxwell equation to bend light, you need simultaneously change here magnetic and electric properties of the medium. And only metamaterials, which allows to introduce these two types of resonators, would allow you to do that. It's not just the dielectric rings. Properties here should be transformed simultaneously to change magnetic and electric response of the structures. At some stage, this field was developing so rapidly with so many ideas that my friend and colleague Nikolai Zholodov from Southampton University wrote this short perspective in 2010, after 10 years, this field was developing, and he put it like apples on the trees. You see that this old concept, which we developed in 2 years, 10 years, artificial magnetism, negative index, and some new concept we're developing. But some years later, actually in 5 years later, when he was asked to write something similar, he discovered that one tree is not enough, and he put a garden to actually show what will happen in this field. This field actually was developing too rapidly, but was lacking applications. After 15 years of developments, it was a very important meeting in the place when metamaterials were born, was organized by David Smith, one of the first author of that first experimental paper, and a big discussion at that meeting was about application. Why it was very important? Bill Gates, whom you know very well, actually invested first 20 millions to actually develop possible applications in this field, and then he invited David Smith to lead some of this research, and it was very interesting discussions where this research was going after 15 years. And during that time, it was some initial discussions, and several companies appeared which are based on the concept of metamaterial. There's a few examples. You can actually find them on the website. I still believe they exist. So basically, these companies were dealing with security, satellite communication, radars, and these are several websites you may check. Particularly, one of my former students was involved in this company, so I know what they are doing. As example of currently, there are, to the best of my knowledge, there are 22 companies based on the properties of metamaterials, and I will briefly explain you, for example, what is the concept of what is the concept, for example, behind one of the companies. You know, in airport, of course, it sounds like a big joke because we are not traveling, but in the time we were traveling, it was a really bottleneck to pass security control. So the proposal of this company evolved based on metamaterials. These are metamaterial patch antennas, where involved both electric and magnetic response, to have this type of display in the wall, and you're passing through that without any security, and this metamaterial device check something suspicious, elements, whatever we can do, and then of course it's defined suspicious guy, and then this people who is suspicious are checked, and it's usually less than 1% of all these passengers coming through this security control. I remember some years ago, I saw huge crowds in the Beijing airport, but I was lucky because I had the business class and was allowed to enter through different door. But you can easily spend 1 or 2 hours waiting there. Hopefully, it will be useful in the future. So basically, as I mentioned, the idea of metamaterials to have magnetic and electric response, to create materials which will be consistent of these units, and there are many different types of structures you can generate, and you can generate two-dimensional, three-dimensional structures. Negative index I mentioned, and again, meta is a key word in metamaterials, and it's behind of magnetic resonances, for example, associated with splitter resonators. But main problem with these metamaterials is that we have metallic elements, and for metallic elements, as you saw, there are many applications, but not in optics. These applications in radars, of even X-rays, control, and terrestrial communications, but not in optics because of metallic elements. So a few years ago, it was an idea to actually how to improve this concept and apply them in different way. so making metamaterials great again. That was, as you understand, happening about 5 years ago. We came to the field which is now termed Mie-tronics or Mie-resonant metaphotonics. As you see, there is a keyword meta, so we still employ magnetic response and magnetic resonances, but we also involved a new word, Mie. Mie, I believe for Asian people, it sounds like Asian word. It's indeed, there is a province in Japan, Mie, and even in, I think in Indonesia or Malaysia, there is a dish, Mie Horen, which is also has Mie. So, but Mie actually is a German scientist who solved exactly Maxwell equation in 1908. He solved Maxwell equation exactly for a sphere. So it's a sphere. It's from his paper, believe or not, it's 1908. It was hand drawing, no computers. So he looked at the sphere made of some material with epsilon and mu, and look at the plane wave which was propagated in the sphere and scattered by sphere, and solve Maxwell equation. Of course, solution presented by these big crocodiles with special functions, but of course, currently we are programmed by Mathematica, but because we are physicists, we are mainly interested in physical consequences of the solutions. So physical consequences originate from dimensionless parameters, which is size of our object, our sphere, and wavelength of light, and actually it includes all these cases which are very well known in different applications. Rayleigh scattering, geometric optics, when this parameter is much larger. We are interested in the case of Mie scattering. So Mie scattering is when we excite particular modes of this sphere. Modes are presented by solutions of a Maxwell equation for electromagnetic and magnetic fields. There are these coefficients that we discuss magnetic and electric components. And physically, you may understand these modes as the following. Let's jump here. When electromagnetic waves, plane electromagnetic waves comes to interact with the object, it penetrates inside. So this is not metal, so it's dielectric, and wave penetrate inside, and wavelength of light inside becomes lambda over n, lambda divided by refractive index. If refractive index is large, lambda, of course, inside much smaller than lambda of free propagation, and it becomes, and if it becomes comparable with geometric size of the sphere, it excites a mode, particular resonance in the sphere. And this resonance is observed in the scattering cross-section as particular peaks. And this is the first peak, actually, in the classical Mie problem, which is more than 100 years old. We notice much later that the first resonance is actually magnetic dipole resonance. This is a dipole mode in the magnetic field, and it produces peak because wave penetrate and excite this particular mode. The second resonance is actually electric dipole resonance. And to see the importance of dielectric particles, I start from the beginning of that slide and will show you scattering efficiency from magnetic and metallic and dielectric particles. If you have a metallic particles of 50 nanometers, surface plasmon polariton produces sharp peak, but dielectrics are not involved. And if you increase the size of the particles, then size of the particles is very bad for plasmon polaritons because we driven by surface, and you see these resonances become very broad for silver and gold, but instead for silicon, we observe this sharp resonances similar to what I described with discussing resonances in this structure. So now immediately we got an idea that we can take this resonance, magnetic and electric, and apply the whole machinery of the metamaterials to look at average parameters and change mu and epsilon at will, engineering different structures. This is fine, and initially people thought, okay, this is a good way to go. Let's expand this concept to dielectrics, and we'll do the same what we were doing for plasmonics. However, during last few years, we discovered that this field is full of interesting discoveries, and it produced completely different ideas and concepts. Why it's so? I will try to explain you on that simple drawing. We have dielectric particles of several hundred nanometers. So it's not a small particle like 20, 50 nanometers like in the plasmonics. This is dielectric particles, and it's large enough to excite different modes. So first mode is electric dipole mode. It's a D displacement vector. Then magnetic dipole is for magnetic component, also dipole. Electric quadrupole is the next mode, magnetic quadrupole. So these large particles of several hundred nanometers support different kind of modes. What will happen if our electromagnetic wave will simultaneously excite several such modes? These modes will interfere. They are not orthogonal, and they interfere to produce different type of radiation pattern. And this interference completely change our understanding of what happens with waves excited from such kind of antennas, dielectric antennas. And this shows you, it's from a review with my former very brilliant PhD student who is now in Changsha, in the military academy professor, and its schematics show what will happen if you interfere a different type of this multipoles. Electric dipole, electric quadrupole, the most famous, of course, electric dipole and magnetic dipole. I will explain it to you in a second. But you see that different multipoles produce different patterns, and these patterns are such that you can actually create unidirectional scattering. And this is remarkable because interference usually considered in physics as an effect which generated by two sources. If these two sources are too far, of course, no interference occurs because they will attenuate. So you need to place the sources close, but not close enough, with the distance of order of quarter wavelength to see the strong interference pattern. And that was studied in many applications of waves. Here, interference produced by different type of dipoles, so we can see strong interferences from a single particle, and this is called Kercher effect. I will come to that in a second. Then wave penetrate inside of this object and excite material, so we may see a lot of enhancement due to these resonances. Then we engineer near field effect. And in addition, as we discovered recently, we can actually have a so-called bound state in the continuum, very interesting new type of effects associated with interferences. Kercher effect, that's why I mentioned that if you have an electric dipole and magnetic dipole simultaneously excited, we can see strong interference, and if their amplitudes are identical and phases right, then we can see unidirectional scattering. This is a result of interference when we actually suppress wave from one side. To understand that, we do it in steps. For example, if I take a plane covered by dipoles or electric dipoles, they will emit, each of them will emit to both sides. The same with magnetic dipoles. If I put them on a line, they will emit to both sides. So this is very well known. If you have a source, we emit to both sides, but this single particle can support two types of these dipoles, both electric and magnetic. If you combine electric and magnetic dipoles, what you will see, you can observe unidirectional scattering. So because of this interference, you have a line here, or plane covered by two types of dipoles. They cancel radiation from that side, but they enhance radiation from this side. So this is a very remarkable phenomenon, which was predicted by Kerker in 1984, again, purely theoretical, and it was actually, that time, it was absolutely no mean to verify that, but he just figured out that property from analyzing Maxwell equations. But here because we excite multipoles of different origin, we can see this effect in experiment and generate them in the lab. I mentioned about another interesting feature associated with multipolar effect, bound state in a continuum. This is a very interesting effect. This is very interesting feature, which also has a very long history. In 1929, pioneers of quantum mechanics, von Neumann and Eugene Wigner, we published a very strange paper. At that time was a development of quantum mechanics. We look at the solution of Schrödinger equation and found a strange solution, which we now understand it's strange because it does not correspond to fully localized eigenmodes. So to explain the solution, it's quite strange because it's exact solution. I will use a kind of cartoon drawing to explain what is the physics of that solution. If you have a quantum mechanics, particles in quantum mechanics, usually free propagating particles is possible at the above of potential well, but if you place quantum particle inside of potential well, it will get trapped. It will correspond to discrete level of energy. And this is a very well-known textbook type of discussions of beginning of quantum mechanics, a classification of a continuum and discrete states. Where bound state in a continuum appear. Imagine that we will modify this potential. We will modify this potential in a way that we will have this oscillating edges of the potential. Then quantum particles, of course, can be fully localized in the potential well. It will be propagating above any potential, but in between maximum and zero, our particle wave function will experience reflections and transmissions with different phases, and it's possible here to construct solution which will be fully localized. But this solution will be above zero energy, so it will be sitting inside of a continuum spectrum. So this kind of modes are known, these days are known like embedded modes or bound state in a continuum. Embedded means that we stay in the continuum spectrum. So this feature are also very important for this Mie-resonance, this Metaphotonics, as we observed during the last few years. This interest to bound state in the continuum in optics was generated through years, and first, even it was initially brought to optics around 2008. A first experiment was done in 2011 when people observed this type of states in the waveguide arrays. So two defects generated waves in the band of these waveguides, but proper compensation. Hello?
Oh,
I guess you're not sleeping. And then we can make a break in 5 minutes because it will be logical stop somewhere. So generated waves compensate each other. And it was a lot of activities in this field in photonic crystals, in photonic crystal slabs, when such states appear naturally in the spectra, What is important about state, because this wave is fully localized, it corresponds to very high quality factor. So, and quality factor means that the wave is highly localized. To understand the physics, let's look at the modes of the slab waveguide. In the slab waveguide, we have leaky modes propagating right and left. And if I introduce corrugation in waveguide, corrugation means that I will change refractive index periodically on the upper and lower surface. Then I open the band gap. This is so-called Bragg reflection band gap. And when I open a band gap, I create different type of Bloch modes. So interesting that for one case, Bloch modes generated by these two periodic structures enhance each other. So we can constructive interference. And from the other side, Bloch modes cancel each other. So we have destructive interference. And modes get fully localized in this slab. So this is an example of the origin of the bound state in a continuum of periodic corrugated structures. So in fact, we can see actually destructive interference in far field means that we almost don't see radiation from such states. This is shown here in a simple cartoon. You see that modes stay there, no radiation because it's symmetry and time reversal symmetry. But this is not the only example. It's not the only example of this highly localized states, bound state in a continuum. And the other, I mean, there are four mechanisms. This is a second important mechanism to create such states. If you have two different type of modes and their dispersion cross each other, we basically come to avoided crossing. And usually avoided crossing dispersion, we associate it with what people often call dark states. So dark states are actually bound state in a continuum, because dark states means that you can't couple by external radiation to that state. This is a special type of bound state in a continuum based on interference resonances, was predicted in 1985, and this, again, the paper from Germany. And that's what we are employing, using here for many of this Mie-resonant problem. To explain before break, I will explain you this, and then we can make a break, because I guess it may be a bit longer. So let's look at the single resonator, the electric resonator. Of course, if wave penetrate inside, it's similar to Mie sphere. It can be classified from Mie solution, but if I take one size changing, so I will increase height of this resonator, then basically when height will be a quarter of wavelength, I will see an effect which is called Fabry-Perot reflections. So basically, vertically, I will have Fabry-Perot modes, and horizontally, I will have a Mie-type modes which are predicted by Mie theory. By combining this type of modes, I will again achieve some of the interferences as strong coupling. That's what we discovered a few years ago, and we discovered that if you look at the modes on the aspect ratio plane, we observe this strong coupling regime points where these two dispersion collide and create this point with dark states. These points with dark states correspond to very strong concentration of energy. So we call it high Q, high quality factor modes. And this high quality factor modes actually allows you to push resonant properties of isolated resonators very high. And that completely change the range of applicabilities of such modes. The states we observed in microwaves. This is a resonator which vary in height, made of ceramic with high refractive index. And you see these peaks correspond to this strong coupling regime. A quality factor is 12,500. And we also observe it in near infrared experiments in optics. Here, of course, quality factor is much less, but still for nanophotonics or subwavelength photonics, quality factor few hundred is an extremely high value. Why we are doing that? Why we are interested in that? First of all, we are very much interested to have subwavelength localization of light for miniature devices and for nanophotonic circuits, to have just elements which will be installed in your, for example, watches or cameras, and will help to do a lot of useful functionalities like testing or even blood sugar testing at home or on go. So we need the small elements. For that, we need to push these footprints of these devices to much smaller values. If you look at micro scale, micro disk, micro rings, we can have a very high quality factor, high localization for micrometer size. Plasmonics, surface plasmon polyritones, allows you to squeeze light to very, very small resonator volume or very small footprints, but quality factor or quality to trap light in resonator becomes very, very low. Mie-resonances allows you to do a bit better, but they associated with much larger footprints. The idea to have this bound state in a continuum and interference of modes allows you to achieve really subwavelength localization with a high quality factor. The next step, which we are doing, it's increase it even higher using several array of several resonators, and currently we have predictions and the first demonstration of extremely high quality factors, again originated from this interference of Mie modes in different resonators. I can stop here, just natural stop for break, so let's do break. Is it okay?
It's okay, yeah.
Yes.
5-10 minutes? 5 minutes?
5 minutes? Okay, yeah.
Okay, okay, good, good.
Okay.
Yeah.
Hello?
Hey, yes, yeah.
Are you back?
Yeah.
Shall we continue?
Yeah.
Yes, please.
We can continue.
Sorry if it's getting difficult. Yeah, I try to move simple, and then I don't hurry. I try to explain more. Anyway,
That's fine. Yeah.
so we come to the second part, which is devoted to metasurfaces. I specifically call all dielectric because I will be discussing metasurfaces based on dielectrics and explain why it's dielectrics which is make all metasurfaces so famous. First of all, when Federico Capasso, one of the inventors of this word and field, visited us in Canberra, I borrowed one slide from his talk. He doesn't show it anymore, but that was how he used to explain metasurfaces. Imagine that we have a plane wave approaching some particular surface. Then it's illuminated by waves, and it emits waves from every single point of the surface. It's so-called Huygens principle. And then if I modify the surface in some way to change emissions of these elementary units, I produce different type of secondary wavelengths, and I can redirect my beam in a different direction. Of course, this Huygens principle in that formulation does not tell you what will happen with reflection, but it can be applied. But anyway, what is very important that to achieve this effect, we need to structure that surface, to introduce subwavelength structure into that surface. This is similar to diffraction grating, but diffraction grating is usually periodic modulation of refractive index. But here we just can do any modulation. It will be characterized by effective K vector and with a different phase profile introduced on this along the surface. Because elements of the surface much smaller than wavelength, remember about this meta concept, but where we may be in resonance and non-resonant, we basically dealing with very thin surface, which in geometric optics is just interface. But we can change any direction of the scattering waves. This means that we again come to the modification of textbooks. One of them I mentioned about negative index. Textbooks are not wrong, but they're not complete. Science is going on. So the famous Snell's law, which says you that reflected wave will be reflected on the same angle as incoming wave, is wrong, because if I change the surface, this reflection will be dictated by the properties of this surface. And that metasurface initially was suggested with that concept to actually change beam propagation, beam reflection, to control direction of propagation of wave from the surface. But later, it was incredibly expanding field, and currently this is a sketch from our recent paper of the Cheng Wei group in Singapore, when we discuss few directions. It should be published, the invited mini review should be published in Nanoletters in several weeks. You see that from initial suggestions in 2011, when we just metasurfaces were considered like a phase discontinuity planes, based, of course, on some earlier achievement for creating subwavelength grating or space variant gratings. You see, field is so broad, but we pick up only 4 fresh directions. So the biomedical applications, I will mention some example today. Then quantum applications, a very recent emerging field. You see the years 2020, the first papers were published in 18. And then computational information metasurfaces with digitalized image operation, and very recently emerging field of combination of metasurfaces, which are planar structure with 2-dimensional materials, such as TMDC materials. So it's extremely broad field. But particularly me and my collaborators are concentrated around 2 streams, which we support through this metaphotonics concept. One is stream is to have a metasurfaces based on multipolar interferences and interference generation. And the second stream is to use resonances. I basically was telling you about that, for example, of isolated nanoparticles, isolated antennas, but now this concept actually expand to the field of metasurfaces, which are 2-dimensional planar structures. We'll do it step by step. Resonances. As I mentioned, this Kerker effect is extremely powerful concept, but to have an efficient Kerker effect, we need to have a superposition of electric and magnetic resonances. If I start from Mie-sphere, as you saw from scattering data, electric and magnetic resonances do not overlap. They just have different locations. If I move from sphere to disk, in disk changing 2 parameters, diameter and height, I can move resonances. We discovered that a few years ago, absolutely accidentally, and we basically understood that we can control these resonances. My former postdoc, Isabel Stoide, who is now junior professor in Jena, she went to Sandia laboratory and was fabricating structures, and she fabricated like more than 50 different structures trying to play with resonances. And we discovered that overlap of resonances, magnetic and electric, which occurs and basically observed in both transmission and reflection. When we superimpose these resonances, our metasurface becomes Huygens metasurface. Each element of this metasurface transmit wave in one direction and reflect waves in another direction, or just don't have any transmission because it's a compensation of radiation pattern. So in that sense, we can construct metasurface which will allow you 2 pi phase coverage. Why 2 pi? Because it's based on 2 resonances, electric and magnetic. Each resonance brings you pi phase difference, and combining 2, we have 2 pi difference. And because of this Kercher effect and the Huygens conditions, we have a very high transmission. Almost no reflection, very thick absorption, no polarization conversion. And that's a metasurface with high transmission. However, you understand that these conditions occur very special points when we overlap resonances, and how to make this metasurfaces broadband. It's also very interesting physics I will mention to you, and this physics is based again on the possibility to control 2 types, Fabry-Perot and Mie-resonances in such post. If I look at the one element of this metasurface and will change height, basically initial conditions when resonances overlap, it's on a log scale presented with this very sharp curve. This is the conditions when we have a transmission achieving for specific polarization, achieving 100%. But if I increase height, I actually trap second resonance, and this is observed here like second resonance, which is satisfied Kercher condition. Now, each of these Kercher condition achieve 100% transmission, but it's a narrow band, is a very narrow region of wavelength. If I work somewhere here, in between these 2 resonances, I will still have a very high transmission, but I will have a very broad operation of this metasurfaces. This is a roughly idea behind of this highly transparent metasurfaces based on physics of Mie-resonances and their possibility to extend them to support several Mie type of resonances in the dielectric rod. If you look at different metasurfaces suggested by different groups, you will observe that plasmonic metasurfaces have a very thin elements. You don't need that interferences, but the electric metasurfaces have a relatively high post because we need this kind of additional guiding mode in the post to achieve high transmission. This idea is shown here for specific devices we demonstrated some time ago. This is a transmission over wavelength. You see the very, very broad operation, and it's shown here on the aspect ratio when you see this domain of very high transmission which we can employ for specific device. Specific device is a half-wave plate, quarter-wave plate, which are usually quite expensive to buy for and being based on different principle. And also phase modulator based on liquid crystals are used to imprint particular phases, but now phases can be printed by simply designing a proper metasurface. Now, this is an interesting table which shows you evolution, recent evolution of these metasurfaces, in particular judged by transmission efficiencies. And this is 2012, one of the first metasurface devices suggested. I remember the first paper was 2011, and that suggesting lenses axicons based on plasmonics. The gray color show plasmonics, and you see efficiencies, transmission efficiencies are very, very low. And holograms, first holograms is incredibly low efficiencies. Then people change from gray color to blue color, or bluish color. Blue is a dielectrics, and dielectrics immediately allows you to increase transmission efficiency. And you see that different type of transmission efficiency achieved for different devices. What kind of devices? Meta lenses, vortices, hologram, Q-plate, beam reflector, beam deflectors, axicons. These are all type of devices which can be created based on this simple one-layer metasurfaces. Up to now, the highest transmission efficiency is about 91–92%. This is very close to transparency of a glass plate. You should remember our resonator are all placed on a substrate, which is usually silica glass. And the records belong to our group because we actually approach it from the very deep physics of optimizing transmission instead of just applying brute force calculation. I will show you a few applications of metasurfaces just to expand your horizons, and one of them is actually employ photonic, multi-mode photonic fiber for communication. There is a current trend to actually use not single mode but multi-mode fibers and imprint information not only in frequency but also in mode profiles. So it's called not wavelength division multiplexing like usually, but mode multiplexing for multi-mode fibers, and that can be done by employing simple holograms and propagating in a fiber different modes which generated by these holograms. For these 2 quarters, we have a very high transmission which covers all telecom bands, and that can be employed for fiber experiments, which was done a few years ago in collaboration with our colleague from Chalmers University, with very high transmission efficiency. Instead of a relatively big setup to imprint these profiles, we just use a simple metasurface composed of 4 types of units to imprint different small holograms to multi-mode optical fiber. The second big things which is happening now is application of metasurfaces to quantum problems, in particular to quantum light sources by combining, for example, with metasurfaces with 2D materials and with photon manipulations and non-classical detections. Metasurfaces can be employed for different quantum functionalities. We have a perspective paper just came out in Nature Photonics. The second idea to employ metasurfaces, as I mentioned, is to use resonance. This is extremely important property which allows to introduce new functionalities, and in most of the cases this resonance is also associated with the bound state in a continuum. So to understand this bound state in a continuum, let's imagine that we have a metasurface which covered by these elements. The elements will be a bit tricky. You see that each element has a kind of asymmetry parameter, asymmetry properties. This is tilted bar, this is shifted hole, this gaps shifted, this is different lengths. So why we need that? So the different papers introduce some structures and we try to discuss it on the different physics. But in reality, this feature is related to broken symmetry of elements, allows you to introduce so-called quasi-bound state in a continuum. What is that? If I have a wave propagating normally to the surface, if our elements are all symmetric, this will be purely dark state. So wave will be not coupling to surface. If I break symmetry by introducing the shifts asymmetry parameter, I couple normally propagating wave to modes of this metasurface, but I couple it in a very specific resonant way because asymmetry parameter controls the value of this coupling. We analyze different types of metasurfaces and put everything on one single curve. As you see, it's perfectly fit the main features of this bound state in the continuum, produce this very sharp resonance, and then the sharp resonances can be placed in any point of this parameter curve as show asymmetry parameter and wavelength, and can be employed for different type of applications. People started to fabricate different structures, and this is examples of such structures. We need a surface which composed of elements with broken symmetry. This is a notch. This is a stop. This is 2 different widths of these bars. Bars are identical, and we produce sharp resonances in transmission, allows to control this reflection and transmission features of metasurfaces. This metasurface allows you very high Q factors, This evolution of Q factors for resonant metasurface presented here currently is demonstrated by a group from Guangzhou. It's 18,000. We don't need such high Q factors. We need just a few hundred to have a very useful applications. One of the applications which we suggested, and now it's developing by several groups and already have a patent and some prototypes, is so-called applied to pixelated metasurfaces for biosensing. The concept is the following. We have a metasurface which consists itself by smaller metasurfaces. Each pixel is just a metasurface composed of the shifted or tilted bars. Tilting, as I mentioned, is produce a symmetry parameter. A symmetry parameter produces a sharp feature, but we scale all these metasurfaces by not changing angle, but changing size. This means that we move this resonance along the particular frequency band. So in this particular example, we have a scaling parameter which allows you to scale them, these sizes, and this produce a range of this resonance comb which can be employed for sensing. The idea is that we can, when we put analyte on this metasurface, it change our transmission properties. And depending on vibrations in mid-air, this change occur for specific wavelength, for specific wave numbers. Every substance which we put there will have a specific feature for this intermolecular vibration type of activities. And then in our comb of resonances, we will see a characteristic profile which will be a feature of fingerprint of this particular analyte. This fingerprint features can be mapped on a barcode, particular this barcode metasurface with scale smaller metasurfaces. And then we can actually look at the spectral composition. If you have a library of these spectral images, we can look without any spectrometer, just in a very simple imaging system. And then we will know what kind of substance is there through its resonant interaction with the metasurface. Basically, it produces different type of absorbance curves, which can be again classified from molecular barcoding and the specific library for identification of substances. You see that metasurface here plays a crucial role because it allows to introduce in mid-air very sharp resonances, and then scaling produce a comb of resonances to be applied for specific sensing operation. Of course, we can employ this sensing through angle. It's also a type of things, and we can actually go to much more complicated sensing operation, employing hyperspectral biosensing, separating different spectra. One more application of metasurfaces I wanted to mention today is enhancement of different effects through this formation of bound state and continuum resonances. This example from our recent paper shows that we use two-dimensional material, which is one of the bigger family of materials here, and place it on a resonant silicon metasurface to enhance second harmonic generation. Silicon metasurface, of course, composed of silicon with inversion symmetry, does not allow to generate second harmonic, so it does not influence second harmonic generated from two-dimensional material, but it allows to support hotspots through this excitation of bound state in the continuum modes and enhance substantially second harmonic. So in this particular work, we saw 5 orders of magnitude enhancement of second harmonic through this excitation of hotspots for bound state in the continuum. I wanted to say and emphasize that people familiar with plasmonics we of course know that concept of hotspots is extremely valuable in plasmonic. But here we somehow replace that concept by two types of mechanism. One is the excitation of Mie modes. Second is interferences of Mie modes to create hotspots and highly resonance response. So I come to conclusion. I don't still feel audience, as you can imagine, and level of your training, but I wanted to emphasize that what you watch now, it's interesting developments in the field of metamaterials, which currently it's already 20 years old and evolved from standard homogenization parameter metamaterial to new field, rebranding field, tronics or metaphotonics, which employ this optically induced magnetic resonances, but employed for different in different way and for different applications. The key feature now is high refractive index elements which support resonances, as I mentioned, and we can base different type of devices and metasurfaces on these resonances by employing materials like silicon, germanium, high index materials, which are actually already been for a long time for serving optics community. And new features, as I mentioned, in addition to use of Mie resonances, this is new physics of bound state in the continuum, which found a new life, as I described, and may be very interesting and useful for application. I stop here. So if you have some questions, I can address some question now, or you can, the most brilliant students can write me to this email together with your professors. Thank you very much.
Thank you. Thank you for the talk. Okay.
Was it very difficult?
Actually, I'm not working exactly in this field, but I can understand some of the content. Yeah. Okay. I think because I'm not working in this field, but I how to say I understand 50 to 60% of the.
Okay, okay, not bad. Thank you very much.
Oh,
I
actually,
didn't waste my time.
No, not at all. Actually, we have a lot of audience from other platform. In this conference room right now, we have 44 people, but we still have a lot of audience on other platform because we are broadcasting your lecture at different at two other platforms.
Okay, thank you.
Okay, yeah. Any question from the audience? So
yes, hi, Professor Yuri. Okay, for me, I have a question about the metasurface and the nonlinear optics. So is the real advantages by using the metasurface to enhance the nonlinearity?
I did not mention much about nonlinearity. Even I just first discovered that your course about nonlinear optics, but I thought that it's too hard to move to nonlinear effect. Yeah.
Yes.
Okay. Yeah, that's true. Because when you have this, first, why nonlinearities are important here? I remember I was attending annual meeting of German Physical Society, DFG, and it was a talk about observation of second harmonic in plasmonic structure. And I asked the guy, what is the efficiency of your second harmonic? He looked at me and laughed and said, oh, the fact that we observe it, it's already great things.
Okay.
Because it's really efficiency of all these plasmonic structures is extremely low. It's 10 minus 11, 10 minus 10. And that's because field does not penetrate inside of metals. In dielectric, field penetrates in the side of dielectrics and get advantage of materials. Plus, it can be enhanced through resonances because at subwavelength scale, we don't have this famous quasi-phase matching condition as QPM, which people used for generation of second harmonic in for example, in poled lithium niobide waveguide for much larger structures. We have much thinner structures. We don't have QPM, but we need to be careful with the mode matching, and that's very important. First, resonances in both harmonic and fundamental, and then mode matching. And believe or not, this in our science paper, our conversion efficiency 0.1%. This is a huge difference between any plasmonic system. And then people believe that, and you combine all resonators in a metasurfaces, then you will get a collective response, and we can achieve convergence efficiency of order of a few percent from metasurface. And that would be great achievement for many applications. So basically, I think nonlinear nanophotonics will gain a new life from that, because we employ a completely different concept. Even nonlinear nanoplasmonics was known for ages. Its application were very, very limited. Yeah.
Okay, thank you very much.
Thanks for asking. Yeah, but sorry, I just avoided nonlinear effect. So many groups actually pushing that, and one of the idea was also to employ both nonlinearity of metasurfaces and nonlinearity of this two-dimensional materials, which can be enhanced and basically controlled. But it's ongoing research. Yeah.
I see. Yuri, I have a question. It seems to me that most of the meta devices and metasurfaces are designed to work at 1.5 micron, the optical communication wavelengths. I guess it probably is hard to shift the operation wavelengths towards more shorter wavelengths, say like visible wavelengths. Actually, my question is, for your Mie-resonator-based meta devices, so is it scalable? My point is, if you shrink the structure by a factor of 2, does the operational wavelengths also decrease by a factor of 2, so that you can immediately shift the operation wavelengths to visible wavelength range? Is that true?
It's not true. Why? Because we are, of course, all the electrics are scalable. In that sense, you're absolutely right. But in terms of a particular phenomenon, it's not exactly right, because we are searching for specific resonances. So as I mentioned, when wave penetrate inside of material, wavelength becomes lambda over n, and lambda over n should be comparable with geometric size. So in terms of Mie-resonances, yes, they are scalable, exactly like you said. But in terms of bound state in a continuum, this is a specific type of interference effect. So we need to, it's not simply scalable, because if, for example, I take my post with a strong coupling and this dark states and try to scale, it may, this strong coupling point may be completely removed, because it's a combination of several scales. It's not just simple scaling. But in terms of Mie-resonances, yes, you're absolutely right. So it is scalable. Most of the, unlike plasmonics, which depends very much on a very tricky dispersion, most of the dielectric problems are scalable, and that also allows to verify many of these ideas in microwaves. So we just come to the concept, and for example, unidirectional scattering, and you use not optics but just microwaves, and we understand that in optics will be very similar, because dispersion of refractive indices is very weak, very different from plasmonics. Yeah.
I see.
But so, no, it's not true that 1.5. 1.5, first of all, our experiments, 1.5, because first of all, we were part of a big center of excellence, which were dealing with the communications, KUDOS, which was for 15 years. And that obviously we were interested in telecom applications. But no, people demonstrate different. For example, now there is a there is a very big wave to fabricate metasurfaces for mid-IR. Of course, they are much bigger, but of course, or terahertz. Terahertz is fine, but in many types of optics is still not available for terahertz range. But mid-IR is very important for applications. So it depends on applications. And then people were crazy very much about meta lens, and obviously meta lens was very important for visible. But again, as I mentioned, scalability somehow around everything. But again, materials, for example, silicon is not good for visible. So it depends on materials. So for 1.5, it's fine. But if you go to visible, silicon is lossy. And then people use titanium dioxide, for example, for many meta surfaces operating invisible. But in principle, yeah, we can do meta surface at any scales and any dimension and any wavelength. Of course, some design principle may be slightly modified.
I see. Okay, so there's a question from audience. Okay, I'll read the question. What is the difference between dielectric array and whole array in dielectric slab?
Ooh, very smart guy. My congratulations. So we had that question some years ago, and there is difference, of course, but there are a lot of similarities, of course. So we look at the slab. Of course, in a single disk, we have Mie-resonances. Of course, people know about Babinet principle that we can match Hall and resonator and Hall, and we know that the electric dipole will switch to magnetic dipole in a Hall. But in reality, we look at these membranes with holes, and we discovered that a lot of machinery known for normal metasurface can be applied there. But we look at the solid places between holes, like resonators, and actually you can even do multiple expansion for these structures. We had a paper in Advanced Materials last 2 years ago discussing that. So, but it's a different field. People use different languages, but in fact, there are many common things in terms of presentation, multipoles, and everything. Yeah. So there is difference, of course, but there are also many similarities which not many people still realized.
I see. Okay.
It depends, of course. If you look at the Venn diagram, from Venn diagram point, they are identical, just periodic structures of the electric materials. But I'm talking about resonances, this interferences, unidirectionality. That requires specific approaches for both of them.
I see. Okay. It seems right now we don't have input questions, but I guess if the audience have questions, they may send you email. Okay.
Yeah, I'm email guy. I'm not a WeChat guy. I'm
okay.
or SMS guy.
Okay, thank you. So let's thank the speaker again, and thank you very much for the nice lecture. We really appreciate it.
Thank you.
And, thank you.
I saw something. Okay, thank you very much. Thank you.
Thank you very much.